So I'd like to cover a couple questions regarding sort of using conversion factors in order to solve questions which ask you to solve for something in terms of another thing. And essentially the idea is that we want to find within the problem some kind of common ratio which itself can be viewed as a conversion factor. And as we go through, predominantly we're using the mole conversion factor, but you can think of this as a proportion as well. So for the first question here, it essentially asks us, what is the mass in grams of a single atom of oxygen? So clearly it's, if we're looking at, the question as a whole, the ratio that we're looking for, the conversion factor that we're looking for is from grams to atoms. So at the heart of it, we're really looking for grams to atoms. Now, there are several conversion factors, but the sort of the main conversion factor if we're looking for grams to atoms is using the Avogadro's conversion factor. And the idea here is that if you have any particular element, for instance, if we were to consider oxygen in this case, if we have any particular element, the atomic mass in AMU, if you were to take that many grams of the element, that would essentially translate into 6.02 times 10 to the power 23 atoms. And so that proportion itself gives us a conversion factor. So if you were to sort of write this out, you would essentially say that, okay, oxygen, which has an AMU, an atomic mass unit of let's see here, so you have 16. 16 is your average atomic mass, but also if you were to take 16 grams of oxygen, that would essentially equate to 1 mole. But recognize that your mole in this case, that's not the conversion factor that we're looking for. We're actually looking for a conversion factor which involves atoms. But the thing to recognize here is that 1 mole is actually 6.02 times 10 to the power 23 atoms. So we could sort of express this as being 6.02 times 10 to the power 23 in terms of atoms. So these are our atoms here. And that's the conversion factor that we have at hand. So if we want to find the mass in grams of a single atom of oxygen, this is the conversion factor that we'll use. So what this tells us in terms of conversion factors is that I could have any amount of oxygen. I could toggle the amount of oxygen and I can tell you how many atoms there are in that many grams of oxygen. Or I could toggle the amount of atoms and I could tell you correspondingly how many grams of oxygen that would be. And so this is a little powerful here, and you could make a conversion factor. You could say, okay, well, so you want to know how much a single atom is, and this is at the heart of using the conversion factor. You say, okay, well, you have 1 atom, right? And you use your conversion factor in such a way that your atoms cancel out so that you're left with grams. The only way you could do that with these two values is if you were to take the number of atoms, which is 6.02 times 10 to the power 23, you would take those atoms, and of course you want to express this as grams, so you could do 16 grams of oxygen. Your atoms would essentially cancel out, and what you would be left with is 16 over 6.02 times 10 to the power 23, which is Avogadro's number. And if you were to multiply that, you would get your answer in grams. And this as a whole would be 2.66 times 10 to the power 23 grams. And so that would essentially be our final answer for this question. Now, the next question, it's a little more complicated, but it sort of abides by sort of the same answer in this case, or the same method. So it says, what mass of mercury has the same number of atoms as 64.2 grams of calcium? And, again, if you look at the question, I mean, the first thing that really stands out in terms of looking at the units is that, if we're talking about mass, what mass of mercury, we're clearly alluding to grams in this case, right? And so, you know, our conversion factor, it's essentially going to include grams to atoms, right? Grams to atoms. And so you're just, you know, you're scanning and you're looking for any kind of conversion factor which can give you sort of an amount of grams equated to atoms. And it makes sense to think that the Avogadro ratio, you know, would give you this particular ratio. And why that is, and again, we're revisiting sort of the periodic table. Calcium, if you were to find calcium on the periodic table, you could see that its atomic weight, its atomic mass, is 40.08. So if I were to take 40.08 grams and sort of translate that into atoms, that would give me 1 mole. And we know that 1 mole is just 6.02 times 10 to the power 23 of anything. So in this case, it would be atoms. So it would be 6.02 times 10 to the power 23 atoms. And so you could see that 40.08 grams of Ca is going to give me this much amount of atoms. So this is sort of, this is a ratio. This is, again, a conversion factor, which can help us work backwards in this question here. So, but how would we use this, right? First, we want to figure out how much is 64.2 grams of calcium in atoms, its atom equivalent. And once we figure out how many atoms of calcium are in 64.2 grams, then essentially what we would do is we would just say, okay, what mass of mercury, right, is that many atoms of calcium? So the first step here, I mean, really at the heart of it, the first step is to find out how many atoms are in 64.2 grams of calcium. And the idea is to know this particular conversion factor, because we know that 40.8 grams equals 6.02 times 10 to the power 23 atoms. Now, all we need to do is ask ourselves is, how much is 64.2 grams of calcium, right? How much is 64.2 grams of calcium? So this is a conversion factor which we can use. So if we toggle the amount of grams of calcium, we can find out how many atoms would correspondingly be produced. And if we toggle the amount of atoms in this case, we could find out how many grams that would be. So in this case, we're going sort of left to right, where we're toggling the amount of grams and finding out the amount of atoms. And so what we would do in this case is we would, again, sort of use our conversion, and we would take what we want to know in terms of its conversion. And so we want to use our conversion factor in a way that the conversion cancels out, or really the grams cancels out, and it's expressed as atoms. And so what you would do in this case is you would say, okay, well, I'm going to take my amount of grams and I'm going to play with my conversion factor in such a way that my grams cancel out. And so the only way that's possible is if you put the grams in the denominator, and of course have your atoms here. And if you were to solve this, if you were to do 64.2 over 40.8 multiplied by Avogadro's number here, you would essentially get 9.64 atoms. So you'd get 9.64 times 10 to the power 23 atoms. So that's essentially the amount of atoms. So we could sort of write sort of an equivalent here. Therefore, 64 point, let's see, 60, so 9 point, okay, so it would essentially be 9.64 times 10, or let's work in this way. We'll say that 64.2 grams of calcium has 9.64 times 10 to the power 23 atoms. And so that essentially would be our conversion. But again, this is sort of an intermediate answer because our job is to find out what mass of mercury would have these many atoms. And so the idea here is to sort of go on to step 2 and then say that, okay, well, you know, I know that 64 point, let's see, I know, well, okay, so you have your number of atoms. You have Ca equals, let's see, 9.64 times 10 to the power 23 atoms. And the idea here is to say what mass of mercury has these many atoms. So again, you're looking for a ratio of grams, right? Because you want to talk about mass in grams. What mass of grams of mercury is this amount of atoms? So you are again sort of using a conversion factor that is allowing you to make a proportion between grams and atoms, but it has to relate to mercury in some way. And so the idea here is to again recognize that you're dealing with mercury, a new element, Hg, which has its own atomic number. And this is, of course, us trying to sort of get the Avogadro ratio here. So if you were to look up mercury, you would essentially find that you have 200.6 as your atomic number, or actually your atomic mass. And that would imply that if you were to take 200.6 grams of mercury, you would essentially have 1 mole atoms, or you would have 6.02 times 10 to the power 23 atoms. And so the idea here is then to essentially use this conversion factor to solve for how many atoms would be in, or how many grams would be this amount of atoms. So really you're saying, what you're really saying is that 6.02 times 10 to the power 23 atoms is 200 grams of mercury. If you then said that you have 9.64 times 10 to the power 23 atoms of mercury, how many grams would that be? And so it's apparent that you're dealing with conversion factors. And you use your conversion factor to say that, okay, well, I'm going to put what I want. So 9.64 times 10 to the power 23, I'm going to put what I want here. And I want to express it in terms of grams. So between this conversion factor, you're only going to put what would cancel out in the denominator, right? And so you'd have 6.02 times 10 to the power 23 atoms. And you would use your, you would essentially use your gram conversion. And what this would do is it would put 9.64 times 10 to the power 23 over 6.02 times 10 to the power 23, and you'd multiply that by 200, and that would essentially give you your, it would give you your gram equivalent. And your gram equivalent would come out to being 321 grams. So again, you know, we're just using these conversion factors to allow us to be able to express x of A equals x of B, and then we can toggle A or B in however much quantity we want, and we could essentially work our way backwards to finding one thing expressed as the other. So in this case here, you know, sort of moving on to the next question, it essentially asks us how many moles are in this amount of molecules of Na2SO4. So the idea is, you know, looking at the question as a whole, instead of relating, in these previous questions, we were relating atoms to grams, it seems. Now we're relating moles to molecules. And the special thing about the mole is that it can be expressed, it could make a ratio of atoms, it could make a ratio of particles, and it can even make a ratio of molecules. So the idea, you know, sort of in this question is that can you use the Avogadro ratio to find out how many moles are in Na2SO4, and that's essentially a polyatomic ion, because we essentially have 3 atoms individually sort of combined together. So really the ratio that we're looking for here is moles to molecules. And if we're going from moles to molecules, we would essentially want to use that ratio, that would be our conversion factor. So we know that there's, in 1 mole, we know that there would be 6.02 times 10 to the power 23 molecules. So it applies for molecules as well. It's not exclusively just for atoms. In 1 mole of, let's say, pens, there would be 6.02 times 10 to the power 23 pens. So 1 mole is just this amount, which we call Avogadro's number, of anything. So in this case here, 1 mole would equal these many molecules. If you changed the number of molecules, how many moles would you have? So, so this is sort of the same thing here, where this is our conversion factor. And we are then toggling the amount of molecules and asking how many moles. And this is, of course, consistent with what we said before, where I said that you could sort of toggle the amount of the left or right-hand side, and you could find the number of the corresponding amount. And that is, of course, despite the unit that it's expressed in. So if we were to say, okay, I'm going to put what I want, 5.35 times 10 to the power 22. If I were to put what I want, and then what will I put in the denominator here? Well, I'm obviously going to have to put my molecules in the denominator, because I want my molecules to cancel out. So that's just going to be 6.02 times 10 to the power 23. And of course, these are molecules, right? So these are the units of molecules. And I'm going to put my 1 mole here, so that once I cancel out my molecules, I will be left with a problem of basic arithmetic, which is going to give me the amount of moles. So your answer here is going to be 5.35 times 10 to the power 22 over 6.02 times 10 to the power 23. And of course, once you do this division problem, you're essentially going to get a particular amount of moles, which is going to be 0.0888 moles, and that would essentially be your answer. So again, it's just using conversion factors to be able to work our way backward. In this case here, where we're asked that, we're told rather that a container holds 31.87 of carbon, how many moles does the container contain? And again, just sort of looking at the problem as a whole, we're essentially looking for a conversion factor which is going to equate moles, and it's going to equate grams. And so, the conversion factor here is apparent that we're going from grams to moles, or you could think of it as moles to grams. As long as you can find out this proportion, it would make sense. So if we're talking about carbon in this case, and we look at carbon on the periodic table, carbon, in terms of its atomic weight, is 12.01. That's the atomic mass, which is also sometimes called the atomic weight. And we know that, we essentially know that 12.01 grams of carbon is going to, essentially, let me write an equal sign. It's going to equate to it's going to equate to 6.02 times 10 to the power 23 atoms. But again, we're not really concerned about the ratio grams to atoms. We're concerned about grams to moles. So why don't we go ahead and write this as moles? So we'll say that we have, this would essentially be 1 mole. And this is consistent with Avogadro's ratio, because what it says is you could take any amount in grams, well, not any amount, but if you were to express the atomic mass of an element in terms of grams, that would be 1 mole of that element. So in this case, you're just toggling the amount of grams, and you're trying to figure out how many moles you would correspondingly have. So if I had 31.87 grams of carbon instead of 21 or 12.01 grams of carbon, how many moles would I have? And again, this is a basic ratio where you take what you know. So you know that you have 31.87 grams of carbon. And what would you put in the denominator, and what would you put in the numerator? Well, in this case, you would obviously want to put the, you want to express this as moles. So you want your moles in the numerator, and you would take your, you would essentially take your grams of carbon, so that your grams of carbon cancel out, so that when you do this problem, which is going to be 3187 over 12.01, once you do this problem, you're essentially going to have your answer expressed in moles. So that's sort of the reasoning behind why we're putting what in the denominator or what in the numerator. So for this next question here, it's asking us how many grams contain this amount of zinc atoms. again, if we sort of abide by, the process that we've been working with, we're essentially taking our grams of atoms, or we're essentially we're making a proportion between um, our grams and our atoms. So for this one, let's see here. So we're going from grams to atoms, and we know that Avogadro's ratio allows a proportion between grams and atoms. So our grams, if we were to look at zinc on the periodic table, we would have Zn, that's the chemical symbol, and 65.39 would essentially be our grams. So if we were to magnify this, if we were to say that 65.39 grams, that amount would have 6.5 times 10 to the power 22 atoms in it. But we know that that number is sort of synonymous with 1 mole. So we could say that 65.39 grams equals 1 mole. But in this case, we want atoms, right? So instead of writing 1 mole, we could just write the atom equivalent, which would be 6.2 times 10 to the power 23. And then, of course, you could toggle the amount of any one of these and sort of get a corresponding answer. So if we were to say that, okay, well, how many, if we were to say that, okay, we want to know how many atoms there are given this proportion, well, we're going to write what we want to know, which is 1.4 times 10 to the power 21. And in the denominator, we're only going to put that value, which is going to cancel out. So 6.2 times 10 to the power 23 is essentially going to cancel out in terms of atoms. We want it to be expressed in grams. So we're going to put our gram equivalent here. And our gram equivalent, if we were to do this as a problem, we would essentially have to take 1.4 times 10 to the power 21, and then divide by this number here, which is 6.2 times 10 to the power 23. And then we'll multiply by 65.39. And of course, this entire thing would be expressed in terms of grams. So again, that's just a basic ratio. Now, for our last question here, what is the molar mass? I don't think that's the last question. I think there are a few more here. But if we're trying to find the molar mass, really, a distinction can be made in this case. We have a molecular mass, right? If we have a molecular mass, and there is also something called the molar mass. Now, the molecular mass, if we had, for instance, H2O, the molecular mass of this compound, and it is a compound, what we would do in this case is we would take the amount of, well, let me try to break it down. If we had NaCl, right? These are just one atom of each. We have sodium and we have chlorine. So the idea here is we would take the atomic number of sodium, which is Na, and then we'd essentially just add that to the atomic number, or not the atomic number, but the atomic mass of chlorine. So the atomic number of one element plus the atomic number of another element. And that would essentially come out to being our molecular mass. So if we were to do this in the case of hydrogen, you want to understand that hydrogen actually has 2 hydrogen atoms. So if I were to take hydrogen, one atom of hydrogen, which has 1.0078 as its molecular, as its atomic number or its atomic mass, I can't just add that to oxygen. Oxygen's atomic mass, which is 8, I think that's 16, because that would not be an accurate atomic. That wouldn't be the accurate molecular mass. And the idea is that you have 2 hydrogen atoms, so you actually want to multiply the atomic mass of hydrogen by 2. So your number would actually come about to being, it would be 2 times 1.008 plus 16. So that's essentially what you would get in that case. So in the case of, so that's molecular mass. Now, molar mass is essentially the exact same thing, but it's on the scale of grams per mole. Now, what I mean by that is if I have H2O in this case, I'd essentially do the same process. You know, I'd take 2 and then I'd have 1.0078, and then I would add that to oxygen, which would of course be 16. And instead of, you know, this unit, the molecular mass is in terms of AMU. The molar mass, however, is in terms of grams per mole. So if I were to add this up, if I were to get, let's say, you know, 32 or 33 something, that would essentially be on the scale of grams per mole. So 33 grams equals 1 mole of a 33 grams would equal 1 mole. So essentially what this is saying is that 33 grams, if you were to take 33 grams of H2O, you would essentially have 1 mole, or in other words, 6.02 times 10 to the power 23 molecules of H2O. See, at this point, we're not talking about molecules of, we're not talking about atoms, right? Mole in this case is not referring to atoms. It is instead referring to molecules. So you want to keep in mind exactly what you're referring to when you're using the mole. But in this case, we would obviously be using, for molecular mass, that is, we would obviously be using the grams per mole unit. So if it's asking us the molar mass of this particular polyatomic ion here, what you want to remember is that these are actually 3 individual atoms. If it were K2C and then lowercase o, then we could sort of say that this is potassium and cobalt. But in this case, since these are 3 distinct atoms, of course, marked by being an uppercase letter, you could say that this is potassium, and this is of course chlorine and oxygen. So you want to find out the atomic mass of the average atomic mass of each and every one of them, and that would essentially give you, once you add that up, the grams per mole of that amount would essentially be your answer. So if you were to take K here, and K is potassium, if you were to take K and look that up on the periodic table, you would essentially get a particular amount, and I'm not too sure sort of what that amount is. I think it's I found it here. It's 3.10 AMU, so 3.10 AMU. And you would get your chlorine as being 12.01 AMU, and you would get oxygen as being 16.00 AMU. But really, we're not talking about AMU. We're really talking about grams per mole. So instead of having these as AMU, in terms of molar mass, we're talking about grams per mole. So would you just add these all up and then express them as grams per mole? No, you wouldn't. You would obviously want to take into account the fact that you have 2 potassium atoms, so you would have 2 times 39.10 grams per mole, and then you would add that to, so you only have 1 atom of chlorine in this case, or actually I think it's carbon, and so carbon would have 12.01 grams per mole. And then you would add that to 3 oxygen atoms, which would be 3 times 16. So if you were to eventually do that, you would get 138.21 grams per mole. And essentially what this means is that for every 138.21 grams, you essentially have 6.02 times 10 to the power 23 of this compound, or of this polyatomic ion. So in this case here, how many moles of carbon are there in these many atoms? Again, this is just sort of a simple conversion that we talked about here, where if you look at the overall question, we're comparing moles and atoms. So we're obviously looking for a proportion between moles and atoms, which is obviously going to be Avogadro's ratio. So we know that in Avogadro's ratio that 1 mole essentially equates to 12.01. Well, 1 mole would essentially equate to how many atoms? Well, for each and every case, it would be 6.02 times 10 to the power 23 atoms. So if you were to essentially toggle the amount of atoms, you could use this as a conversion factor. So if you were to say, okay, well, I have 4.1 times 10 to the power 24 atoms of, in this case, you have carbon, you would want to work with your conversion factor in such a way that your atoms cancel out. So you would do 6.02 times 10 to the power 23, and you would have your mole in the numerator. And then once you do this problem, once you do 4.1 over 4.1 times 10 to the 24 atoms over 6.02 times 10 to the power 23, if you were to do this division problem here, you would in fact get 6.81 moles. So that would essentially be your answer. Your atom unit would essentially cancel out, and you'll be left with your mole equivalent. So this is an interesting question, and I think it's our last. But the idea for this question is, this is obviously a molecule. If we were to read this question as a whole, we're essentially being asked how many grams in these many molecules of this compound. And the idea is, we want some kind of ratio that essentially equates grams to molecules. Now, that's not something that we've noticed so far, and we haven't noticed it because we've only ever been the ratios that we've dealt with so far are from grams to atoms, or of course atoms to grams, or moles to grams, or moles to atoms. So these are sort of the conversion factors that we've been working with so far. This one is from grams to molecules. So the approach here is to find out, and this is obviously a molecule. So this is a molecular compound, and it's a molecular compound through covalent bonds because obviously this nitrogen is a nonmetal, and oxygen is a nonmetal as well. And so when you combine them both, they interact through covalent bonds. And since there is a di prefix here, you know that you're working with two nitrogen atoms, and pent is essentially 5, so you're working with 5 oxygen atoms. So if we were to find the molar mass in grams, or grams per mole, you could essentially make a conversion factor there. So, you would essentially take your grams and equate that to your to the number of molecules that would essentially be. And you want to remember that that if you're dealing with moles, you could essentially have 6.02 times 10 to the power 23 molecules. So so this is sort of inflating our scale a little bit. And what you would do in this case is first you would find out what is your molar mass. And your molar mass in this case is going to be, well, you have nitrogen, and you want to remember what the AMU, or the atomic mass, is of nitrogen. In this case, it's 14.01 AMU. And of course, you want to know how much oxygen you'd have. In terms of its atomic mass, you would have 16 AMU. And the idea for calculating molar mass would be to add these both and express them as grams per mole. But the idea is that you actually don't have just one nitrogen atom, you have 2 of them. So you want to multiply this by 2, and you want to multiply this by 5. So you'd essentially have 2 times 14.01, and then you'd add that to 5 times 16. And then if you would do that, you would have 108.02 grams per mole. Now, of course, this is an intermediate answer because we want to be able to say that, okay, well, how many grams do you have? So this is an intermediate answer because it's not giving us the conversion factor yet. You actually have to write that out. So you could say that, okay, 108.02 grams is essentially equivalent to 1 mole. But in this case, since we're dealing with sort of the context of the question and the fact that we're dealing with a compound, tells us that that we wouldn't have 1 mole of atoms, we'd have 1 mole of molecules. And that's essentially what we were looking for, is to find a conversion factor which equates grams to molecules. And of course, now it's just a matter of using the conversion factor. So if you could toggle the amount of molecules, you could find out how many grams you'd have. And if you toggle the amount of grams, you could find out how many molecules you have. So in this case, I want to go from molecules to grams. So I'd essentially I'd say, okay, well, um, I have these many molecules. I'd say 2.05. I think that's times 10 to the power 23 times 10 to the power 23 would essentially, I want to express my conversion factor in such a way that my molecules cancel out. So I would say I have 6.2 or 0.2 rather, and that's just 1 mole of moles. 6.02 times 10 to the power 23 molecules, and you would have 10802 grams of just grams. And so once you would do this problem here, you would essentially be left with a fraction that, if you were to simplify it in a calculator perhaps, you would have 36.8 grams as your final answer. So really, there are, so you could sort of write your final answer as being that that for that 36. So it was asking how many grams are how many grams in these many molecules in this much of this compound. So you would say that if you had 2.05 times 10 to the power 23, you would essentially have 36.8 grams of N2O5, which I believe is sodium something. It's a polyatomic ion, basically. And so that's how we're using conversion factors to sort of summarize this out. If you have x of A, right, equated to x of B, you could toggle the amount of B and then get how much A that would be, or you could toggle the amount of A and then get how much B that would be. And so that's essentially what we've been doing by sort of using some of these proportions that were given in terms of theory. We know that if we were to take the AMU grams of a compound or of an element, then that would be 1 mole, which is just 6.02 times 10 to the power 23 of something. And so that is eventually our approach.